Welcome to this episode of The World Around Us. In this episode, we're going to look at pedigree diagrams and try to figure out how to use them and how to make sense of them and work with them for a little bit. So what is a pedigree diagram? All right, well, pedigree diagram, it is all the people in a family, and in that family, we're going to look at different traits. I'm going to call it the blue trait and the brown trait. And so we're looking at the blue trait over here, we're looking at the brown trait over here, whatever that means, that's what we're looking at. And the purpose of the pedigree is to look at the traits and look backwards from the traits to figure out what the genotype is. Now, you know, in Punnett squares, there's 6 different versions of Punnett squares, and the Punnett squares give us, like, what are the genotypes, and then down inside the boxes, predicting what the phenotypes would be. So in a pedigree, we're doing the opposite. We're looking at the phenotypes, whether the trait is expressed or not, and using the phenotypes to sort of like reverse engineer back to figure out what the genotypes are. And it's a really good system. For the most part, we can figure out almost everybody. There's some people sometimes we can't quite figure out exactly, but we can get a really, really strong idea. And what we're going to do with this information is, knowing the genotypes of the people involved, we can then predict what's going to happen in future generations. And so geneticists use this information when they're counseling with people. All right, so how does it work? Well, the squares are the males and the circles are the females. The people with the trait are colored in. Now, what we need to do in order to solve what I call the puzzle of the pedigree, and all we have to do in order to do that is to find one parent set with a child who's different. So one parents who have the same phenotype and a child who has a different phenotype, and we're going to find that right here on this one. We're going to have these parents do not have the blue trait, whatever blue is, and this child does. So these are the people in this one, same people over here. These are the same people tracking different traits. So here we have the trait is expressed and this child doesn't have it, and here we have the trait is not expressed and this child does have it. So this is what I call the like parents, different child. That is to say, the phenotype of the parents is the same and the phenotype of the child is different. When we do that, we are ready to now, we can do a couple of things, and 100% of the time, because there are 6 different Punnett squares, and of those 6 Punnett squares, there's only one case where the parents have the same trait and the child has a different trait. And the only way that can happen is if the parents are heterozygous. That is to say, we're using B for our gene. So both of these parents must be able to pass that other B down. What is that other B? Well, let's go ahead and we're going to put the genotype, because we know 100% of the time, if we have like parents and a different child, the parents have to be heterozygous. We're going to write the genotypes in. Big B, little b. 100% of the time, if we have like parents and a different child, the child is homozygous recessive, double recessive. This is the only way we can get a different child from like parents. It's the only way. You can go through all 6 of the different possible. See, there's 3 different possible genotypes: double dominant, heterozygous, double recessive. There's 3 of those, taken 2 at a time. In any Punnett square, there's 6. That's math. There's 6 possible Punnett squares. So of those 6, this is the only case where we can have the same parents, different child. Once we know that the person expressing the trait is double recessive, we can go through and mark everybody expressing the trait as double recessive. And when we know that everyone who has the trait is double recessive, we know that everyone else has at least one of the dominant genes. We don't necessarily know what the other gene is, but we can go through and we can say that everybody has at least one of the dominant genes. Now sometimes we can't say what the other gene is. Sometimes we can. So in this case, we have to look at the offspring and maybe make a guess. Not necessarily, this could be big B, this could be big B, and this could be big B, little b. We know though, this guy had to get a little b from this guy, so that's gonna be big B, little b. We still don't know what that one is. This guy had to get a little b from this guy, so that's big B, little b. If we do the same people looking at a different trait, now we have like parents who have the trait and a child that is different 100% of the time. No matter whether we're tracking the trait and find parents with it, or we're tracking the trait and find the child with it, these guys are still heterozygous. Big B, little b. And the child that's different is always double recessive. Everyone who has the same shading as the child has the double recessive. And everyone who has the same shading as the parents have at least one of the dominant, because the parents are dominant. Now, a lot of times the question is the trait we're tracking dominant or recessive? We'll get to that in just a second, because it's obvious when we look at it after we've filled it in. We're putting in more information than we need. This person has 2 recessives, so this person had to give them one. And this person is coming from someone who is double recessive, so he has to have at least one of the recessive. We still don't know what that person is. These are the same people tracking the trait. In this case, we're tracking the recessive trait. So if the question were, in this pedigree, is the trait dominant or recessive, we would look down here and we would say, we're tracking the trait. If the person with the double recessive has the trait, then it is a recessive trait. In this case, we're tracking a different trait. The person with the double recessive does not have it. That means that the trait that we are tracking is dominant. That's all you have to do. The question is going to be, is this trait dominant or recessive? And sometimes we'll say, is it autosomal or is it sex-linked? After you have found like parents and a different child, you know the answer. 100% of the time, like parents with a different child, these are heterozygous, this is double recessive, 100% of the time. The only way you can get a child that's different from the parents is if the parents are heterozygous and the child is double recessive. One of the confusions about pedigrees is that people think, well, we're tracking the dominant trait. We're not. We're tracking a trait. The colored in square means the person has it. So in this trait, whatever blue means, it's not eye color, because eye color is polygenic. But the blue trait, if you have the blue trait, these 4 individuals have the trait, which happens to be, because of the way this little red circle worked out, recessive. Over here, we're tracking the brown trait. And if you have, in this little circle here, these people have the trait. Everyone that's shaded in has the trait. This person does not. This means when we're looking at this little configuration here, like parents, different child, the like parents are always heterozygous. The unlike child is always double recessive. That is to say, homozygous recessive. All right, that is the what I call the pedigree puzzle solving system. And hopefully that will help you as you work on these things. You're going to see these on standardized tests and stuff like that. Find the like parents with a different child. And that's going to be either they don't have the trait, the child does. They do have the trait, the child doesn't. The parents are always heterozygous. The child is always double recessive. That's it. That's how you do it. Thanks for watching. Please click the like button, subscribe to the channel, sign up for notifications, all that stuff. That's it. We'll see you in the next episode.